we're looking at marks on our DNA that correlate with changes over time. And so the idea is, of course, is that you can have someone who, their biological age, or excuse me, their chronological age may be 40 or 45 years old, but then we can calculate a biological age from their epigenetics, which may be several years younger for someone who is in quite good health, made very good health or lifestyle choices over the course of their lifetime. So chronologically, they may be 45, but biologically, they could be 40 years old. And of course, the converse is also true. So you could have a similar 45-year-old who may be, heavy smoker, didn't get a lot of exercise, or take care of, was not able to get good sleep throughout the course of their life for different reasons. And they could have a biological age that's actually accelerated compared to their chronological age. So maybe like 50 years old, something like that.
Right. So for myself, I've had cancer. I had cancer at 41, thyroid cancer. And I actually had this conversation with a couple of colleagues of mine in this industry. And they're like, oh, well, you know what? You should be happy with that. I was like, I was kind of disappointed. So if I look back at my history, my health history, the fact that I've had cancer, would that be something that would be part of my results, or have an impact?
It definitely could. There are studies looking at this. So cancer does associate with acceleration of the epigenetic age. Okay. So this could be really due to a couple of different reasons. So maybe just really as a sheer consequence of the disease. So your altered epigenetics as a result of cancer, they could alter then the biological clock. Similarly, it's been shown that a common treatment for cancer is chemotherapeutics, and these they're very powerful drugs in many cases and can have lots of systemic effects on your body. One of which is to help kill or control the cancer, but other adverse side effects as well. And as a result of this, it could also affect. It's been shown to affect the biological age as well.
Interesting. Okay. Well, I never had chemotherapy, thankfully, and I didn't have to have radiation, thankfully, but I guess just that cancer marker. Now, what about if I used to be a smoker, which I was many years ago? Would that have an impact?
Yes, smoking is associated with age acceleration, biological age acceleration. Okay. However, again, we're talking about epigenetics can be reversed. And so it could be that, if you were quit early enough, or you've spent a long time as a non-smoker, your epigenetics could reset and you could have the younger or the healthier sort of a biological age. You can reverse some of that damage. That's possible.
Okay, so what exactly, now people are going to ask, DNA methylation, what does that mean? So we talked about epigenetics, we defined that. What about DNA methylation?
So DNA methylation is a type of an epigenetic mark. It's the most common and thoroughly well-studied type of epigenetic mark. So what this is just a single carbon. If we can really look at the organic biochemistry, it's a carbon group added to your DNA. This occurs typically on cytosins in DNA, almost exclusively, in fact, in humans. So functionally what it's doing is it is helping to regulate or control gene expression. So genes need to be turned on or off in specific time and space, and epigenetics really helps to accomplish that. So I think a good example to illustrate this is, so all of the cells in our body have the exact same DNA sequence, yet we have really specialized tissue functions. So we have eye cells that help us see our vision. We have skin cells, liver cells that carry out metabolic functions. So we have all these diverse activities or functions that our body is able to do, despite having the exact same same genetic sequence. And it's only because epigenetic mechanisms are able to turn these cells into an eye cell or a liver cell or a muscle cell, heart cell, that our body is able to be able to carry out such diverse activities.
Okay, so correct me if I'm wrong. I'm just trying to put this in layman's terms here. So if I was born, let's just say I carry certain genetic predispositions or SNPs that maybe I'm predispositioned to have celiac disease. The right environment, the right situation could possibly turn that on. Does this make sense to you?
Yeah, that's possible. Yeah, that's certainly possible. So you're right. So you bring up a good point. So people can have certain genetic predispositions, but it's not. There's many situations where we know it's not guaranteed to lead to a certain disease, right? So the BRCA allele, breast cancer allele, BRCA. So if you carry this certain type of gene, SNP, like you mentioned, you are at a higher risk of developing cancer, but it's definitely not guaranteed, right?
Right, because it has to be these perfect environment, and I say perfect in not so perfect ways, like, poor sleep, poor diet, no exercise, bad habits like smoking and drinking, and all of those factors can cause that switch to flip on, correct? Does that make sense?
Yeah, that's correct. I
I'm
think
making it simple, Keith.
Yeah, that's right. Yeah, that's correct. I mean, so you see people, it's not purely just the environment, right? So it interacts with our genetics in very complicated ways. So I think we all hear of stories of, so and so in the community lived to, their 100th birthday, and they say, "What's the key?" And they say, "I have I smoke every day," or so,
Yeah.
something that sounds, wow, that really doesn't sound very intuitive there, but nonetheless. And it could be because their genetics are different, right? So they're more predisposed to a long life, despite these unhealthy activities that these unhealthy habits that they may be engaged in.
Right.
So.
And so your test, the MyDNH, this test actually looks at the markers for aging.
Correct. So I should say we look at a subset of markers. So there are probably thousands and thousands, if not millions, that can be. I mean, so we now know this to be the case, right? So, but in the early days, Steve Horvath, he focused on the data available, and what he found was 353 different DNA methylation marks in the genome that were highly informative for biological aging.
Ah, okay. So this all ties into the Horvath clock, correct?
Correct.
Maybe describe what that means.
Right. So for Horvath's clock, again, he focused on these 353 DNA methylation marks, locations, and at each one, he can calculate a percent methylation. So from 0 to 100 of the methylation level, DNA methylation level at that area and that base in the genome. He then developed a mathematical model to take all those values and output a biological age. So you get 353 different values, you put into an equation, and you get a value in years. So 45 biological years, or 47 biological years, or 68, or whatever the case may be. And that changes based on the DNA methylation values at those sites. And so those change over the course of our lives. Some will increase in value and others will decrease in value.
Okay. And so your test, so how do you know that I would be my age? Like, you're looking at those 353 markers, right? And it's measured by either blood or urine, correct? But blood is more accurate, right?
Yeah. So yes, that's basically correct. So we don't actually need to know anything about you or about any individual who wants to get their biological age measured. We don't need to know. We ask for certain things for our metadata, but we don't need to know. And in fact, we've worked with forensics team, and law enforcement at my parent company's IMO Research, where they're trying to identify people, right? And so we don't know anything about these samples, and we're able to age them. So we don't need to know anything about your chronological age when you were born. We are simply looking at the DNA methylation values at those positions and then calculating a biological age based off of that.
Oh, okay. So I gave you my my blood sample,